uh, obliging and very helpful in introducing me to this particular event. And coming from Pune, I said that I must do this. And I, grew up in Pune and then went to IIT for my college. But I really enjoyed, and I do visit Pune quite often. So let me start to give you some idea. Basically, I would like to give you my outline. I will give you some introduction. Then I will dive into memory aspect. And then I will first talk about the deep scaling. What does it mean? The deep scaling is nothing but scaling of Moore's law. And we have learned a lot from that in this AI business. Then I will talk about the world of variability. No matter where you go, which discipline you select in AI field, there is a variability. And I'll talk about that even in this battery charging stuff that I'll allude to later on. And then from narrow to broad AI for deep intelligence or deep learning or artificial intelligence, whatever you want to call it, and application to neural network and accelerators. And finally, I'll give you my summary, where we are heading for. So I'm going to dive a little bit into circuits. Those who are familiar with the circuits will understand this, but I can give you upper level or higher level description as I go along. So if you take a processor, 50% to 60% is memory, okay? And there is a memory hierarchy. L1 cache, L2 cache. L1 is the fast cache, and the data is moved to L2, and then L3. L3 is off chip, and things like that. So this is an example. What is shown here is the IBM P8 processor. And so you can see the sizes here, right, roughly. These large caches are 512 KB, then L3 is 96 MB, and it is predominantly embedded DRAM. And then you have this 6 transistor cell. This is the circuit diagram of it. And the 6 transistor cell stores the data 1 or 0. And then there are variation of this cell, which is called as 8 transistor cell. And there are 8 transistors, meaning you count the number of transistors here, 1, here there are 2, 2 here, so there are total 6 here, and then 2 here, 8. So this is what it boils down to. And each one, used for purpose, and the idea behind this is to improve functionality, performance, the bandwidth, and also the storage, right? The number of bits, because and this is sort of the origin of I would say re-emergence of AI. So if you look at the memory, and there is a famous song that I always like to work with, because without memory we cannot survive, right? So memories have many connotations, but in the description that I'm talking about or giving you is basically memory hardware. Of course, our memory, when we try to correlate our stuff to neuromorphic computing, we also talk about that memory. So there are a lot of similarities, and from hardware to our neuromorphic cases. But anyway, we cannot mimic a human being. So we are trying to basically, try to sort of follow, I would say, or mimic in the sense that to the closest point. So consider that you have a hardware memory. So what are the challenges in there? And we want to actually select or get it something from our human brain and understand that memory storage, right? Those neurons, synapses, axons, those kind of things. So memory has a power wall. So anytime where you go, so this is the challenge faced in the deep scaling, and that is deep scaling means scaling of Moore's law. From 1.25 micron technology, we are down to now 5 nanometer technology. Imagine, okay, nanometers versus microns, orders of magnitude differences. And so there are power wall, memory wall, and instruction level parallelism wall. So you can see these challenges are there, were there, and every time, every generation when we try to come up with these chips, they were so much improved, okay? And we try to overcome this. So what is this challenge, memory wall challenge? Basically, data movement between core and memory is dominant in big data application. So memory wall is equal to power wall plus bandwidth. And the bandwidth is the technology limitation, non-scalable. So if you plot the bandwidth and the evolution of the application, you see the system requirements are increasing. However, the memory systems offered is almost saturating. I mean, we need innovations here, right? Because there are a lot of applications here. You can see HPC, high performance computing, financial, radar applications, networking, video gaming, all kinds of things require large memories. Okay, and so these are the important factors that one has to. So one of the good paths is the system circuit technology co-design provides a path to this solution. So if you look at from power perspective, why I'm talking about power? Because that is one thing that we are poor right now in delivering. I mean, the attempts are getting made. So if you look at the history, in 1997, IBM Deep Blue, defeated Kasparov in chess. However, there were so many power systems which were used, and the power was 15 kilowatt. Now you go to 2011 when IBM played Watson versus Brad Ritter and Ken Jennings, and Watson defeated Brad Ritter in Jeopardy game.
Excuse me, sir.
9. Hello?
Sir, your presentation should be on the presentation mode and slides are not changing. Sorry for interruption, sir.
Not changing? Wow.
Yeah.
I mean,
yes, sir.
Okay.
The first slide is there.
Oh. Then I'm sharing it, right? I mean, this is the problem I faced here.
Just a minute, huh?
I don't think from my side there is something. Because it says I'm sharing it.
Now it has changed. And on presentation mode, if it is, then it will be more.
Yeah, but I was on the presentation mode. Can you see this slide? Memory is integral part of VLSI circuits.
Yeah. Now we can see.
Okay. Can you see brick wall challenge, which I talked about? Or you don't see it?
Memory is integral part of VLSI circuits that we can see. That slide is right now on the screen.
So bottom line is the slides are not moving.
No, sir, slides are not moving. And put it on the slideshow mode.
It is in the slideshow mode.
But
here, I mean, can you see the full screen?
No, sir.
No, sir. Full screen is not there.
Okay. Let's see. Okay. You're presenting. I'm going to stop presenting here. And then do this again. I don't know what's, because I do this all the time. I have no problem. I'm going to do your entire screen and disable notification, allow. Okay, can you see this slide at least? Brick wall challenge.
Yes, sir.
Okay, I'm going to move one more. Just want to see. Can
Sir,
you see this one?
make it on slideshow mode so that it will be.
No, but I just want to see whether
Yes,
I'm
yes. Now
moving the slide.
changing.
Okay,
When you
now
change, they are changing.
can you see this? This is a presentation mode.
Huh. But
I just went into presentation mode.
yeah, but it is the whole screen should be a slide, but that is not appearing here. F5, if you press, sir, F5, it will be as per our requirement.
Can you see this?
We can see the slide, but it is not in the slideshow mode. If you press F5, it may be possible.
No,
Hello.
this is an F5.
Sir,
F5.
have you selected entire screen or a particular window?
Okay, I selected.
So you have
Second.
selected particular window of the presentation.
Correct.
Okay, so that's why we are not seeing the full screen, because you have selected the presentation window, not a slideshow window. That's why there is a problem.
Okay, so I had selected entire window, entire screen.
Okay, you are supposed to select entire screen, then it will be visible whatever on the screen of the laptop.
It says window or screen to share, but it doesn't give me allow. So I have to go to individual thing like my presentation, PowerPoint.
Okay,
Oh,
if
entire,
it is
okay, entire screen.
open, okay.
Okay, can you see now?
Yes, now your
Okay.
full screen is visible.
Okay, sorry. Entire screen. Okay. Can you see now?
Yes, sir. Now it is
Yes, sir,
perfect.
now it is perfect.
Okay, sorry. So I hope you understand what I said earlier. So I showed a couple of slides. This one was my outline. This is the memory integral part of VLSI. I gave talk about how much memory and why memories are important. They occupy 50 to 60%. There is a brick wall, and the brick wall here is the power wall, and especially in the memory wall, we have certain other problems, and the problems are bandwidth here, power wall, and the system requirements. If you plot memory bandwidth as a function of evolution of application over time, system bandwidth is improving, the requirements are increasing, and however, the memory subsystem offered, there is a big gap, okay? So, and the applications are quite, extensive. So I was on this slide and I was trying to explain to you. So let me just take a minute that why power is important, okay? We are making tremendous progress, okay, in terms of all these computation, big data, analytics, and which is needed for AI and all these networks, right? So if you look at these, the history of this is in 1997, IBM, played this chess against Kasparov and defeated. However, there were many, processors which were used, and the power was 15 kilowatt. In 2011, IBM played using the supercomputer, played against Brad Ritter and won Jeopardy game. However, there were 90 processors which were used, okay, which generated 200 kilowatt. In 2016, Google AlphaGo game was played and it defeated Lee et al. It used close to 2,000 CPUs and 280 GPUs. Okay, it's a graphical processing unit, which plays a role in, it's customized and plays a role in AI. It generated 300 kilowatt. And recently in 2018, IBM Summit computer for AI, which has 200 petaflops, uses, and it has all kinds of fantastic, supercomputation power, and it consumes 13 megawatt. 13 megawatt. That's amazing, that how now power consumption of the human brain is 4 to 5 orders of lower than that of AI machine. Okay, this supercomputer is used for calculate or finding out the compounds for COVID vaccine. Okay, or against COVID, how they can do it, how the supercomputer, computer can do this, because of all permutation combination of, this carbon, oxygen, hydrogen, all kinds of compounds are mixed and, come up with a solution. But if you put it in right perspective, the power of this is 4 to 5 times larger than human brain, and human brain uses only 20 watts. Okay, and brain as dedicated computer, if you use as a dedicated computer, it can do 38,000 petaflops. Okay, petaflop operations. This is 190x faster. So the bottom line is, as you can see, power still, is a key factor in underneath AI. Okay. Now look at the GPUs which were used here. This NVIDIA GPUs, 28,000 GPUs, okay, from NVIDIA, and 9,000 IBM processor 9. So they waste too much, power. So let me dive into the power. And now, so you can see my slides now, right? No problem.
Yes,
I hope everybody can see it. Okay, good. So, so what happens is there is a knob here. Okay, when you plot, how do you reduce power? So the total power, if you just look at, the power, it is, if you want to drop down the VDD, that is the supply voltage of your chip, then what you do is total power will come down nicely. Energy efficiency also will increase, but the frequency will decrease. That's okay, because for training and inference for AI, it takes, we need small, small frequencies, or not very large frequencies like processors, but you can be well below 2 gigahertz without any problem. So this is a little bit of basics. I'm just going to go from basics from deep scaling to to these other stuff. So mainly the power is the you have dynamic power, leakage power, all kinds of power here, right? So switching power. So remember, it's a dynamic power, leakage power, that is standby power, meaning if you say charge your instrument or your unit or appliance, and over the period of time it will leak, even if it is shut down, because the chips inside, there are leaky transistors and they will start leaking. So in order to avoid that, there are various techniques which can be used but one has to understand what component of the power you are trying to resolve or trying to lower. And as you know now, that as the number of transistors increases, the leakage power increases, linearly actually, or even exponentially, not linearly. But So now there are in a processor, in all these chips, you'll find over 15, 20, close to 15 to 20 billion transistors. Okay. I mean, our population is only, the world population is close to 8-9 billion. Now we are exceeding all those limits on the transistor level. That's great. But it creates headache from power perspective. So what that has to do with the memories? Of course, the memories are made up of transistors. They suffer. And what is happening is in this deep scaling, the continual shrinkage is going on. I mean, all that you see, like these cell phones, your watches, smart watches, all these things are nothing but miniaturization of these chips which are used, and the memories that have been driven like this. Look at the sizes. The sizes, going down and down, and we are talking about 5 nanometer technology here. Okay, 5 nanometer technology. So it's just amazing how this is working. But then making those transistors or chips, it is really a very daunting task to achieve functionality, stability, performance, all kinds of things is really very crucial. So again, I'm not going to get deeper into this, but I will just give you highlights that power design, that is low power design, has all these basics here. Leakage control techniques. In memories, we use shorter bit lines. We only select banks which are necessary. Okay. Then there are header footer devices. Then multi-threshold transistors which are used. Then there are extra transistors which we add. Then we do additional boosting. That is, whenever you need boosting that is higher performance, then you just boost your supply voltage. And then when you are not doing anything, you just drop your voltage down. These are the kind of techniques which are used. And similarly for the memories as well. So logic as well as memories, these kind of techniques are used for leakage as well as dynamic power control. And it is important that the VDD or your supply voltage of your chip needs to be reduced. And that is all about this deep scaling. Okay, how to lower power, how to improve performance, how to increase bandwidth. And so there are multiple research areas which have been dealt with and have been published, getting published in this field. So it's just amazing to see. So again, giving you some kind of an idea what is happening here. Let me bring out my pointer here if I can get. Okay, much better. Okay, so as I showed you, this is the 6 transistor cell. So the idea here is we put a sleep transistor at the bottom of that. And what it does is it prevents, when you turn on the sleep transistor, the leakage coming from these guys is minimized or reduced. So what we are trying to do is lower leakage power. So these are some of the techniques I'm describing you. And these are the contributions people have made, we have made all throughout, over 30, 40 years to make scaling possible. Okay, although scaling has been now, very slowed down considerably, and people are trying to find out ways, researchers are trying to find out different ways how to make electronics industry or have resurgence in that area, and AI has become a classic example for that. And then the quantum computing as well. So high performance low V-min circuit technique. Again, it's a crowded chart, but I can only show you that by putting down innovative circuitry, by cutting down these unselected cells or half selected cells, or grouping them together, one can reduce the power from the memory. That is the whole idea. And this is the classic SHMU that you see here. The SHMU in the sense, you know, you have VDD, you have VCS, these are the two supplies. And as you can see, when you bring down this a white area means that it is all passing area, and you can bring down the voltage to 0.4 volt. Okay, industry and academia have been struggling to bring down this supply voltage below 0.7 volt. There are many techniques which have come up, many technologies which have come up over 30 years, which have been helpful in doing this advancement. Okay, so I'm just going to cut down some of the slides because of the time limit and all that. And so if you look at the high performance low power circuitry, another example is this bit line, which is commonly used, on which you get the data out from your memory. So with innovative techniques, you can don't have to precharge this bit line to high voltage, but you can make it supply voltage minus the threshold voltage of a transistor. So thereby the precharge is not as high as VDD, but lower than VDD. As a result, you can reduce the power on this line. Okay, so this is repeated many times because the larger your memory, the larger the size of your memory, the larger saving it will have. Okay, so that's what it means. So these are some of the techniques I'm throwing at you, showing you how the progression has been made over the years. Then there is what is called as a FinFET. The technology evolved from bulk technology, then SOI, silicon on insulator, and then the FinFET. The FinFET is a tri-gate, which we'll talk about it. And it shows that the active power using this technology can be much lower in this. You can see that graph, right? As a function of active cell power, as a function of VDD, you can get significant reduction. So indeed, the technology does help because you can shrink the features, you can shrink the capacitances, and capacitance means power, right? Half CV square. You want to reduce C overall. And this is this FinFET which I was talking about. It is, this is your gate all over. This is your source and this is your drain. The current goes from here to here. And this is surrounded on the three sides. And this is the FinFET or tri-gate, whatever you want to call. This is the capacitance, network of this structure here. And what happens is when you take these, you want to utilize such a technique or such a technology to your benefit in your design. So what we are showing here, what I am showing here is basically, or what we have published in the in the literature, is that if you have a boost clock and you use these transistors in FinFET, then this when this transistor is off, when initially it is turned on, so you get VDD here, or the supply voltage. But when it is turned off, then this is high, the gate to this transistor is high, and this is also VDD. So this transistor acts as a capacitor. As soon as there is a transition like this, from low to high, you will get a glitch here, upwards glitch. So what it means is, you are using a capacitor to glitch up your circuit or power to that circuit. And that is what is very crucial. So you need that higher voltage to get high performance, but only for certain time. You don't need it for full cycle, just only when you need it. That's the whole advantage of this. Okay. So you can see this, right? So you get a glitch when it is on, goes down, and then again, when the cycle is on, and it goes down. So this is the higher power, higher voltage that you see. So using these techniques, you can do a lot. You can do amazing work, and you can improve performance, functionality, also the bandwidth to make your memory circuit stable. And there are lots of these novel ideas, usage of an inductor here by improving the, to get the LC tank, and that LC tank will supply voltage when your clock is off. You can use this LC tank to deliver power to your circuit. So in a way, you're saving power. That's the whole idea behind this, that how to save power. Okay, so again, I'm not giving you, but you can read through these literature, but there are multiple ways. There's a boosting, resonant boosting, then you can have cascaded booster, and then cascaded plus resonant booster by adding an inductor and things like that. Okay, so I will just skip some of these for the sake of time, because I have lots of slides to show you. And so a test chip, it contains the block diagram, you can see, and it has a booster circuitry, and this is the array here, control circuitry, and blah, blah, blah. And then you can get the output. So the results of this, I just want to share it with you. So these are the chip, how it is fabricated. So this is your second generation test chip without, with inductor here, metal inductor. And originally it was large, but we could cut it down nicely to 30 micron, and for our third generation test chip. So bottom line is, you can be innovative in fabricating these chips, and idea behind this is how to lower power, right? And that's what we are doing here. So so hardware data shows that the no boost, or if you don't use the boost, indeed you can get smaller, average current. That's correct. But the delta is not significant. And also you can bring down the voltage quite significantly, actually. Here in this zone, at around 0.4, 0.45, the chips do not even function without boost. So if you use this technique, which I described to you, you can make the chips functional, have good performance at lower voltages, and you can utilize them, for IoT applications. Okay, this technique for Internet of Things, you can utilize this. So these are the ideas that can be useful. And then there are many more attributes of this. Access time, that is the performance here. Definitely using this cascaded boost, you can see the functionality can be achieved way below 0.3 volts, and so on and so forth. So here is the waveforms showing from the oscilloscope, and the functionality at 0.24 volt was shown, and without boosting it was 0.345. So you can see how low we can go. This is just a demonstration. So once we go lower the voltage, what happens is half CV square, right? So V is dropped down significantly. The voltage is dropped down significantly, and as a result, the savings in the voltage, dynamic voltage or dynamic power is much more improved. So, and then this work, this was our work, and we can, this is a table of comparison. But bottom line is, indeed, with all these things, we were able to show a significant progress in that field. Now, another topic I want to bring in. And this is along the deep scaling, okay? And the deep scaling has variability, right? So when we scale, no two transistors are identical. And it means they differ. Now I'm giving you example of transistors. But when you talk about these battery charging techniques, the battery lifetime again goes through this variability. Okay, and I will show you that later on, that no matter however you want to skin a cat or which example you want to give me, there will be always some kind of variability if you are talking about two objects which are placed together. Okay, and that is where these variability plays a crucial role, and predicting the yield of it, predicting the lifespan of it is really challenging. And if you can improve the yield by even 1%, you can save millions of dollars for that foundry. And that is what it boils down to. So exploring the tails of statistical variation distribution for accurate yield estimate is computationally very expensive. And that's where you need fast algorithms. Some of these algorithms can be useful for machine learning. Okay, we can also use these algorithms in combination with machine learning algorithms, and I'll show you like this. So the world of variability has tremendous painful points here. Okay, if you take embedded systems, all kinds of drones, high performance computing, Mars vehicle here, autonomous vehicles, all kinds of things. Then, in the chip, on the package, the coolant also, different temperatures can cause problems. Radiation, soft error rates, alpha particles, right, can cause a lot of variations because it can change threshold voltages. And, in the atmosphere, when your drone is operating at a higher voltages, higher environment, you can see from the takeoff, landing and all that, the temperature would change, and you can see the environmental conditions as a result of it. And then if you talk about the chip, chip has variation in process parameters, lengths, and random dopant fluctuations, where random dopant fluctuations, dopants are used for adjusting the threshold voltages. And these voltages are you implant generated through implantation, and there are very few atoms in your channel. Okay, it's very hard to control it in a foundry environment. These are challenges. So the variability impact and the future of this, in the electronic industry, is, you can see, I told you we started with planar FET, field effect transistors, then came FinFETs, then now nanowires, and then will come all these multi-bridge channels, which are called as nanosheets. Whatever technology you select, there will be always variation. Okay, variation in the threshold voltages, variation in the lengths, variation in the widths, variation in the mobility, all kinds of things. So one of the techniques is this predictive analytics techniques that we developed. It is very important. It could be also a machine learning technique. And as we all know, that Monte Carlo technique is used very heavily in defining or looking at or analyzing the robustness of your design. This is the Monte Carlo technique. If you have two variables, VTN and VTN1 and VTN2, and these are the points where Monte Carlo would like to reach. Okay, that is the high sigma region. So that is 6 sigma, because you want to make your product to sustain to 6 sigma. And this is the area we want to go. But Monte Carlo is a technique which is extremely slow technique. So researchers came out with failure region estimation from sensitivity analysis. So you have two variables here plotted, And what you do is you use worst case scenario. You go only in one direction. That's the sensitivity analysis. Then, but sensitivity analysis is inaccurate because it is only taking you in one direction. Then there is another one which is called as a failure grid point method, where you create grids like this, squares, and then only select points on the grid here. But then again, it is slow and it is inaccurate. Okay. So that's where we came out with a smart predictive failure analytics, where what we do, the idea here is to go in this tail region of a Gaussian distribution, because there are only too few samples here, there are many samples here. So what we do is we use uniform sampling, okay, first a crude sampling technique to generate failure of gravity, meaning the samples will fail, say somewhere here in this region, and then we shift this Gaussian in this region. So automatically we are close to this region. The sampling rate is extremely fast, and it's orders of magnitude. So we were able to commercialize this technique, and we were able to also utilize this technique with the help of machine learning techniques like KNN, nearest neighbor, K-mean technique. All these techniques are combined to form these algorithms. Now, by the way, some of these algorithms are not explored in the battery charging, application. And I have not worked in that field. Could be another way of looking at it. Can we explore this in that domain? So just to give you an example, how fast this technique is. So this is this Monte Carlo technique, which is difficult to get in this region. And here is our technique, mixture importance sampling. And you see the speed up as a function of sigma. We want to reach higher sigmas. So if you look at number of samples and number of samples here, which we call mixture importance sampling, we just require smaller set of sampling, while Monte Carlo requires millions of samples. And the speed up by using our technique is 5 orders of magnitude. So such algorithms are very crucial also in machine learning, and in because the data volume is increasing and all that. So how much time do I have now? Professor Kataukar?
Yes, sir. It is up to 11.
Okay,
So just 10-15 minutes we'll keep for question answer session if somebody is having some questions.
Okay, because I have lots of slides to cover, that's why I'm asking this question. So
still you have 45 minutes, 40 minutes.
40 minutes. Okay, then I have plenty of time. Okay, so applications, domains for pervasive statistical methodology that was used for SRAM, and also the reliability. And again, I'm alluding to the theme of your conference, theme of your symposium or workshop, that some of these techniques can be easily ported into that field. If somebody does good analysis, in that area. So when we took this method and applied to memory application, so what we found that if you take two supply voltages for memories, VCS and VDD, these are two supply voltages, different. One is to the cell and one is to the logic of the memory side, okay, peripheral logic. Here it is word line connected to VDD. So if you take that, if you just connect to VDD, then you get a smaller region of success or operation here, very small. But if you connect word line to VCS, same as your cell. So this is your cell here, and this is your word line. And you connect, if both the supplies are to VCS, you can get quite a bit of passing region, as you can see here. Okay, so larger passing region. So what does this mean? It means that your memory can be made robust by selecting the knobs in your voltages, and this technique can give you good prediction to make sure that your predictions are correct, and that's what it shows. So now what we did was we took the hardware, actually fabricating the chips, and this is the simulated model on the right hand side, and to the left hand side is the hardware model. So there is a close corroboration, as you can see. So the mixture importance sampling predicted hardware trend very nicely. That is the bottom line. So the application to the reliability. Okay, so the reliability is nothing but just like your batteries or charging. Over the period of time, you want to predict the life of it. Similarly, you want to predict the life of a chip over 10 years, 20 years. How do we do that? So there are accelerated techniques. And if you do those techniques, that is temperature as well as higher voltages, if you apply those voltages and temperatures, you can get the end of life of a chip. Now, what does this graph show us here? It's VCS as a function of VDD. These are two voltages on a chip. Okay, the contours that you see here are predicted by that mixture importance sampling technique. All these, blue, green, yellow, red. Red means worst yield. Blue means best yield. Okay. If you do that, and these points that you see here are done through measurements. You apply VCS of this and VDD of this to the chip, to the hardware, and if it fails, it will fall in this region. So thousands of chips were generated, or measurements were generated like this, and it was observed that the predicted values, look at these values, predicted here, these points, they fall in this category, and there is a good corroboration with the hardware measurement and as well as simulated simulations. So what does it say? That the predictions are excellent and also corroborated with the hardware. And this is the power of that technique. Okay, now I want to switch here from deep scaling. I gave you much more information regarding what are the bottlenecks in deep scaling, and especially functionality, performance, bandwidth, as well as variability, right? So, but deep scaling, how do we migrate to deep intelligence? Now, 1940s actually, the AI is not new, okay? We have been doing AI, machine learning for a long time. Machine learning especially has been, for a long, long time. In 1940s, Alan Turing said that there would be some kind of a mimicking of brain or neuromorphic circuit, something like that, or architecture. This was in 1940s. And after that, it grew up, or it ramped up in 80s, sometimes, later 70s and 80s, and then again dropped down. And now Over the decade, it just blossomed again. And thanks to deep scaling because of the Moore's law, to increase compute power, push for bandwidth and performance for AI. And you see the leaps and bounds of growth in applications of AI. And what does this mean? What does AI mean? AI is basically nothing but, it's now you have data, algorithms, and compute. Okay, and what does this translate to? So translating algorithms to CPU architectures, large data needs storage memories, and I gave you almost my heart and my memory pitch into it, and compute requires specialized processors and especially AI accelerators, right? And without these accelerators in the data centers, you cannot do machine learning because the data has increased quite significantly. And so it is mind-boggling, right? What does AI mean, or how does AI span? So AI is basically narrow AI, which we have been doing that. It's a single task, single domain, superhuman accuracy and speed, all these regressions, logistic regression, support vector systems, all these kind of techniques which are used in this narrow AI. Now, broad AI is multitasking, multi-domain, multimodal, distributions, then distributed AI because there are multiple agents working at it, and also it should be explainable. And then general AI, okay? So general AI, that's the part which we are trying our best. We are into broad AI so far, but we are trying cross-domain, learning independently, requires no supervision, solve complex tasks autonomously. These are the kind of things now playing a significant role. And that's what we are doing now. So why AI models become so power hungry? Remember, I told you about chip power. I talked about chip power very heavily because that is the root of making these things. Okay, you cannot ignore hardware to make your software. Okay, the software will follow on this hardware, or you can write applications on that hardware. But if the hardware is power hungry, you will not be able to minimize it unless you do something to it. So traditional data processing jobs in data centers include video streaming, email, social media, all kinds of applications, right? And they are very computationally intensive because it needs to read through lots of data until it learns to understand, because the training is needed. You need lots of data. Wouldn't it be nice to have very less data for training? Yes, that's a very ideal or wish list. It's very hard. Those wish lists are, it's a very hard problem. So one recent model called bidirectional encoder representation from transformers, okay, I'm just quoting here, and it used 3.3 billion words from English books and Wikipedia. So moreover, during training, this BERT or whatever this, translator is, read this data not at once, but 40 times. And to compare, an average child learning to talk might hear 45 million words by age 5, and which is nothing but 3,000 times fewer than BERT. Okay, just mind-boggling that this data is very important. So the data, algorithms, and compute are the ingredients of this AI. So now how we can take these algorithms? So here is a classic example to battery charging, right? So it's a closed loop optimization. This work is from Stanford, recently published, very interesting paper. Okay, how to use machine learning for it. So battery charging is used for, you can cycle the battery, charging, discharging. You can take the data from first 100 cycles. And and you can use based on their voltage levels and the capacity, how much charge is left over, and you can predict the you can get the cycle time of that battery, and you can use this data for training data set using this Bayesian optimization algorithm. In short, how these algorithms are used, the Bayesian optimization, in our case we use mixture importance sampling, things like that. And then based on that, once you optimize it, then you feed the data back, you feed, you train it and then infer from that model and bring back to improve the battery materials and processes. So this is what is happening in this domain. How to charge these batteries faster and utilize the previous data. And that is what I mean by training. And that training samples, if they are too low or too small, the inference becomes, the model development becomes difficult, as we all know. And that's where we need to figure out what to do, how to get the data, and how to remove the outliers and many things like that. So it's all analytics involved here and algorithmic development. So now if you look at the application to neural network of these deep learning operations, you just cannot rely on these algorithms, but you need to have basics. And I'm going to talk about a little bit of that, the material requirements, materials which are used, a little bit out of the scope, but this is giving you some vision what is happening right now in this domain. And implementation, existing non-volatile memories and reach out targets like PCM, phase change memory or other non-volatile memories. So in a deep learning, we all know that there is inputs and there are weights which are generated to account for those inputs. And then there is a summation. Here, there is actually multiplication here, and then there is a summation. And then there is an activation function, like ReLU, sigmoid kind of functions which are used, and then the training is done. And then you infer from it. So the input layers and the output layers, as you can see, and there are hidden layers in between. And there is a lot of data crunching here, okay? A lot of data crunching, from forward path, and then there is a backward path. So in the deep learning network, so you have weights are determined during training, okay? This is the forward path, which I mentioned here. In the backward path, you do the similar things, but you use the delta between the error delta, between the weights and your accuracy of your model, and utilizing that gradient, you can use that to update your weights, which are here. So this is the training cycle. So as you can see, you go forward and backward, right? Forward propagation, and this is an iterative process. So training is very compute intensive. So how do you increase the deep learning performance? So there are various ways. One is what is called as reduced precision or approximate computing, we call it. Sometimes 1 times 1.1. If I say 1.1, but in some application 1.1 is important, but some application we can say 1 is okay. We don't need to sweat to get 1.1, and that is called as reduced precision, and that is translated into your hardware. Data compression and use of sparsity improves the utilization, all kinds of things. And inference and training have different sweet spots, okay? So we have to leverage it. Now, this is all about digital domain. But now when we go to analog computing, So what does it do? So analog computing, meaning there is a discretization. Digital in the sense means it's a binary form, right? 0 or 1. And there are other techniques we can develop. But in the analog domain, you can get discretization. Like if I want to discretize a voltage, voltage could be 0.1, 0.2, 0.3, 0.4, 0.5, like that. But in CMOS, we will have 0 and 1. So how do you get that? Then we have to rely on non-volatile memory elements, and that forms a good solution. And there is a good research going on in this field. And agencies like SRC in US, then government agencies, they're pumping money in this particular field. So I described to you this building block for deep learning, which I mentioned. And there is no need for me to, again, repeat the same thing. So the bottom line is you have multiply, accumulate. Here is multiplication and then summation. Then you are updating your weights. And then there is activation function, which you want to throw away certain things and activate what weights you want to select. And there are different types of functions, okay? Sigmoid, softmax, and ReLU, they are used quite often in the literature. Now, imagine that you have how we can, leverage this kind of computation. If you have a high parallelism, if you can generate that parallelism through a series of arrays now I'm talking about, you have the data and you are storing your weights and your inputs accordingly, then you need arrays. And these are arrays which are shown here. And if you can do that every single array simultaneously, that is called as parallelism. And you can accumulate those currents inside the memory. If you assume that as an array means memory. It could be volatile or non-volatile memory, but we are striving towards non-volatile for the advantages of analog calculations. So if you take that route, then very simple, right? It appears very simple because you apply pulses to your inputs, okay, which is driven, which is nothing but the current is given through these memory elements through Ohm's law. Addition becomes using Kirchhoff's law. And the equivalent MAC operation, will be summation here. Here is the summation operation. And then you store it internally through a capacitor, and that analog voltage is converted to digital. So that's what it boils down to. So using the physics, you can use the memory repetitive elements to calculate the currents, sum the currents, and get your output. And then you can run your, that becomes your great in-memory computation. So I have told you this is the, again here, this is the non-volatile, any memory. You can apply pulses as your inputs, and depending upon your memory style, the pulses, these inputs will be stored inside, because these memories are nothing but these non-volatile memories, especially we'll see that are crossbar memories. Okay, the crossbar memories are straightforward, but they're still in the emerging region, okay, emerging domain, because they're difficult to fabricate reliably. That's the problem. Variability. You bring the topic of variability, describing every time producing the similar result is difficult. That's what is happening. So you apply voltage to these memories on one side. On the other side, this is a crossbar. So voltage on one side and also another voltage on the other side, and you can change the conductance of this memory. Conductance. So if I apply Vx1 here and V delta 1 here, then the voltage will be inside this will be Vx1 minus V delta 1. Okay, so keep that in mind that when you calculate the summation of these voltages, so based on the resistance, now since we are non-volatile memories, there are resistive memories, and this is nothing but an example of a resistive memory that I'm showing here, and this is how you will keep or store the data inside these memories. Okay, now let's look at this non-volatile plethora or domain. So you have all these, which is called as PCM, phase change memories, STT, spin torque transfer, magnetic RAM memory. Again, it's all materially different. How you apply voltages or currents, it will behave accordingly. This is the resistive memory, which comprises of titanium nitride, titanium hafnium oxide, those kind of things, and the CNT RAM. Okay. Excuse me. So now the properties are very critical. The energies, which I said, is very critical, right? I mean, the power. Write times, how fast you can write into the memory, and then the endurance levels. Endurance meaning how long you can write into the memory. How many times you can write into the memory. So the MRAM has this different metallurgy by applying the magnetic flux to it or the current passing through it. You can change the polarity of these layers and make, when it goes in the high resistance state, when with the opposite polarity of these the spins, then you have one state, and then you have in the same direction you have another state. Similarly, in PCM you have a titanium nitride, and here the material is amorphous. You can change from amorphous to crystalline by applying voltage or current here. So things like that. So there are a lot of work which has been already going on and has been also published a lot in this area. So using these memories, you can do a lot and try to get your AI accelerators in a way that it can crunch data, it can crunch, it can take algorithms, and it can compute very nicely along that line. So I'm just going to give you an example here of what is called as a PCM. PCM is the phase change memory, and it is a crossbar, as I said, voltage on one side and also on the other side, and they look like this, and you can store this data in every single thing. Now, if you look at von Neumann criteria or architecture, von Neumann architecture, what it means is that you have a separate multiply accumulate unit and separate memory from CPU, okay, main memory, or L1, L2 cache hierarchy. Now, if you replace your L2 cache, say, using this phase change memory, then you can store the data in it. You can update your memory, and then you can also do the back propagation, which I mentioned, and bring back that thing into this for updating. But then, because of that interconnect, long interconnect, you will be wasting a lot of power here, right? Because you are not doing computation within the memory. So, using this example, you can see the training accuracy plotted against this epoch. Epoch is the number of times the samples are used. So you can get pretty close to the reference values. Okay, this red is the reference value, and this is the PCM model, which is used to generate this. So the accuracy is okay. So another thing that one has to remember in this field is that you need to improve the accuracy as well as you need to have a good bandwidth. Okay? And the accuracy, even if you drop the accuracy significantly for certain application, for example, health sciences, right? Health sciences, dropping the accuracy is not good, because you want to predict, like, when they came up with these vaccines, Moderna or Pfizer, all these vaccines, they test it out. I mean, they use actually, AI to develop all these, predict how much, percentage the vaccine will be, efficient. Say 95% they say, but how about, those 5%, right? So the game here is to improve that accuracy quite a bit. Okay, and that is where you'll see a lot of research papers on the training side, improving the accuracy and also improving power, lowering power. So the MAC, again, the multiply accumulate. Now, if you do that in the same memory, okay, in the previous case, I showed you that the memories and the MAC multiply accumulate units were separate. Now, in the same array, what happens? So this is the array here, and these are the conductances here. Plus means plus sign, and some cells will have a negative data stored in it, positive data, things like that. So what we have done here, we have used that, lowered the power because there are no more interconnects in between, right? So accuracy plotted as a function of epoch, you can see the training accuracy is pretty decent. The TensorFlow, it is compared against the TensorFlow, which is the common platform used, in the literature, and it compares the inference data to this TensorFlow data reasonably well. So remember, this PCM is an emerging material or emerging memory using emerging materials or emerging techniques, I would say, and still you can get decent results. So this is the demonstration, and the authors, Ambrogio, who has published this paper, and I am referencing that one. So now I want to talk about this RPU. RPU is nothing but the RERAM, or resistive processing unit, which is used here, and there are various different models which are compared using this different networks, DNN, deep neural convolution, and long short-term memory-like model. And this RPU, when you use this crossbar technique here and store the data and compute in the memory, what happens is that accuracy is not degraded. The test error is very similar to the FP64 benchmarking, the floating point, double precision floating point. Similarly, the RPU here for CNN network, LSTM, similar, the RPU seems show slightly higher compared to FP64. So these are the kind of techniques which are used, and this RPU-based accelerators, okay, these are called as crossbar-based non-volatile memories, and they work by applying pulses, which I showed you earlier, that voltages on one side and the voltages on their back side, and they can, the difference between the voltages, you can store the conductor, that conduction changes because of their material property, because the application of that voltage, and then you can create a memory as well as in computation as well, because once you turn on that word line, you can read the current from it, and you can sum the current, using those, laws, physics laws that I mentioned, and then you can get results. So you can solve that DNN, CNN kind of networks using these techniques. So so this is this this is the RPU module here, which is shown. So it uses all these methods. Okay, this style, it's a forward propagation, backward propagation, weight updates, all kinds of things. And this RPU chip is 4 to 5 orders of magnitude faster than GPU or CPU. And these are the authors, Gokman and Vlasov, who has published these results. But based on that, one can also come up with what is called as capacitive-based capacitive processing units by using capacitors. This is the resistance, right? Resistive memory. So similarly, there are ideas which can go beyond that as well. So this is all about analog, which I talked about, right? All these memories, non-volatile memories, can store these discrete values of the voltages by applying on their one side, one voltage, on the back side, another voltage, and the delta of that voltage, a corresponding resistance will be stored in that voltage. Now, in that memory. So here, if you use that as the binary, ReRAM, use like zeros and ones, then you can see that the work that we did, it can show, energy efficiency is 176 teraops per joule. It's excellent compared to what is published in the literature. Okay, and here you can see much more area efficiency.
Bhazekar madam, please mute your mobile. Bhazekar madam.
Okay, so so these are the kind of things you can achieve using these techniques, these non-volatile memories, binary or analog, and the trend, the trend is to go for analog memories, and so then what is there? What is the vision now? So in system architectural vision for the cognitive era, here is the, you see the cloud computing, mobile computing with on-demand supports from the cloud here to the swarm. The swarm consists of, drones, autonomous vehicles, your, your wristwatch, smart, smart goggles, whatever, or frames, robots, all kinds of things. And then this mobile stuff should talk to each other. Okay. And what about cloud? If the cloud, if it cannot talk, if it is on the Internet of Things here, then we need to have intelligence between these two guys, this one and this one, this one and this one, so that they can take orders and follow it, or they can give orders back, things like that. So it needs near the edge. If you want to do the near the edge, then on device inference, on device training, low power. See, power is always there. People like researchers would love to have low power than all these politicians who like all high power, right? So we are always looking for low power. Remember that. So so this is the kind of things which are very critical in this world. Now, we were lucky to have a project called Perfect, where we developed a lot of these neural accelerators. And these neural accelerators, we were given a target to reach 75 gigaflops per watt. And we were able to achieve this. If you plot the relative resilience today as a function of technology node, the resilience goes down. It's quite obvious, right? As I said, variability increases, then all other effects, like SCR, then the reliability stuff goes down, and as a result, it goes down. But if you use use modeling techniques and decreasing the voltage techniques, which I described to you, you can easily bump up the resiliency quite significantly. Achieving the target of good resiliency goes up here and achieve 75 gigaops gigaflops per watt. So it is amazing that cross layer optimization, this modeling effort which is shown here is very crucial. All the layers, multiple layers. Along that line, several chips were fabricated. This was the Minerva chip from Harvard. We collaborated with Harvard, and then there was another version of Minerva chip, which was handling these DNN kind of networks and trying to show how low power can be achieved using that. This one was the chip. Again, we didn't publish on it, but we simulated on this one. And this was our IBM chip, which we also were published, which was in 14 nanometer. And we were able to show that we could go very low voltages. And then there were other versions of this as well. So bottom line is, whatever we started out with, showing, taking the network and demonstrating applications on it and proving it with low power. So this is what forms the research area. If you go to conferences, you'll find many people are trying to do this work. Now I want to show you something a little different, and this is hold on. What happened? My looks like there is a problem with the demo here. Here you go, because the cursor was on. Okay, so what happens is how these collaborative robots work, which I gave you a talk, which I talked about, and there the reinforcement learning is very critical, and reinforcement and swarm mentality, how to maintain that. So here you will see some work we did with Georgia Tech and Professor Arijit Chowdhury's group. And so watch this. It's basically, it's a autonomous vehicle which is trained using reinforcement learning. And how does it tackle the obstacles? So bottom line is how this swarm technology, drone technology is marching tremendously. Okay, so you can see those obstacles there kept, but as soon as it goes near it, it knows what is happening to it, and then it maneuvers itself very nicely. See, it goes very close to it. So all these, it has to go to the final path, and the obstructions are moved in different directions, different locations. Now there are two vehicles. So they will look at each other, stop at the See, unless that vehicle goes forward, it doesn't move. And again, the rearrangement of the obstructions and all that you can see. Okay, so you get the point, how this learning and how this is implemented in the chip, how the autonomous vehicle environment and and that work is going on. A lot of companies are working on it. Uber, also Tesla, and many other, folks along that line. So what is the future here, right? So future, if I have to say something about it, if you look at, always remember this number, gigaflops per watt. This is very critical. Okay, and if you look at the number of years on the bottom, on the x-axis, you'll see that industry has been working here. Okay, existing technology for deep learning computation. And that is what? That is GPUs. Okay, or some specialized architecture that you have seen, or some, TPUs that Google has come up with, or things like that are used. So, but they are with digital cores with approximate computing, right? The approximate computing is now getting there, and now the era will be from the accurate to approximate computing for some application using digital AI cores. And then it is going to move to analog AI cores. Okay, and that is why, why is that? Because power. We can play with analog, we can get discretization, we can get better accuracy also if we want. And then in this region, which I talked about, is this non-volatile memories with optimized materials, processes, emerging technology, whatever it's going on. So these are the kind of things which are pushing the boundaries of research and the technology. So I would like to summarize my talk that low power memory techniques described are crucial for energy efficiency. Technology circuit system co-design solution for low power, and that will be the mantra. Okay, no matter what application you select. Once people talk about AI is still at the root. They will ask for power, performance, bandwidth, these questions. Okay, the variability is a important factor, but sometimes we have to live with variability and make the best out of it. Okay, and that is true even in your battery technology. Okay, if somebody looks at it and figures out, because you have to train the model ultimately, right? You have to learn from all these experiments and come up with a model. Then you have to bring that variability into that particular model, or outlie it, something like that. Cost efficient techniques are very crucial, because we all know that to produce the best part at the least cost is the first law of production. Okay, so we have to make sure that it is cost efficient. If I come up with a very complicated technique, then it will not be sufficient to it will not survive. And immense computing challenges associated with the explosion of growth of data-centric AI application will drive innovations in accelerators, which I talked about. In-memory computation, people have been trying this, but it will take its course. It will take its time. Maybe one day it will happen. Non-volatile memories, which I talked about it, right? Why non-volatile memories? Low leakages, low power that way, right? And challenges for selection of appropriate memory materials, memory bandwidth, and architecture, driving inference jobs and ultimately training tasks to power constrained processors on the edge of network will remain. What I mean by that is, if we are talking about the edge, not the cloud, then all these things are of prime importance. And that's where, if you have any solution, if you have anything, work on it. Try to make it practical. Okay. Thank you so much for your attention. I would like to take questions.
All participants are requested to ask the questions. You can put a question in chat box also.
Should I go on the video mode so that they can see me or something?
Yes, sir.
Okay. Any questions? Or did I don't know how much.
Hello.
Yes.
Thank you very much. I have a very simple question related to our Android mobile phones.
Okay.
There is every time versions new are coming up, but they will not last for 2 years or more than 2 years. Why is it so? Is it the handling of the person or due to the chip of the thing?
Okay, so why? The companies want to make money also, right? There is a little bit of marketing stuff, and every 2 years there are different products which come into market. They are cheaper, and everything. A lot of those things are driven by cost. So you have to understand that that particular aspect. So given the fact how the market, like for example, okay, IBM comes out with mainframe or high-end processors every 2 years, because the customers always want to update themselves and they are looking for some kind of performance gain. And that is the reason probably why people are using, these companies are going, and also they can charge more money, right? Marketing in the sense that that's money-making business. Does that answer your question, Subha?
Yes, sir. Thank you. Another small question about the Apple. What is in the Apple chips? They use same chips or different chips? Because they are costing so much.
Right. So, okay. So, look, the cost comes under various forms. Okay. Cost comes in the form of the name, right? Branding, how much demand your product has, right? If somebody wants to buy Apple phone, they have created the ecosystem around it, correct? And they have been there for a long time. Now, do they use advanced chip? Of course. They are like the one that you see in these, advanced phone, they are like 14 nanometer, 22 nanometer kind of chips. They're already there. And that also increases there, but they can offer other options, applications, flexibilities using that particular product. So there are various ways, and then nothing. All those things are not free. So that's where the cost comes from. And some companies charge more because name branding, right? So all these things play a significant role in deciding, those things.
Thank you, sir.
Welcome.
Anybody else having the questions?
Sir, I have one question.
Yeah.
Yeah. So what is the difference between the actual robotics and AI? Generally, in shop floor, we use robots. So is there any difference between robotics subject and AI?
Well, as I earlier said, right, what is AI? AI is nothing but it's like a data, algorithms, compute, and then there is what is called as some intelligence, right? That intelligence, all these things encompass. Yes, that is also part of AI. Robotics is nothing but part of AI, because it have you seen General Dynamics robots?
Yes.
For example, when they walk freely, they dance freely. When you kick them, then they still stand up. How does it work? How do they do that? So they're trained because they learn, and they are, so that intelligence has been given to them through algorithms, right? Meaning if somebody hits it, if there is a bang, then it just takes this as a touch or whatever, that is converted into a reaction, and that reaction is stand up or something like that. That's all programmed. So that intelligence is programmed in there. That is all artificial intelligence.
Thank you, sir.
Okay. There are chat questions. Somebody can read those questions for me, or do I need
Yes,
to do this?
I will read.
Yeah.
There is a question from Dr. Mamata Patwardhan.
Okay.
What are the applications of deep learning in agriculture field?
Right. So actually, very interesting question. In agricultural field, first of all, why do we need artificial intelligence in there? The common sense drives me in the direction that, look, if I have a large number of plants and I want my plants to grow and bear fruits, and after selling those fruits I'll be rich person, right? Is a common sense. Okay, so that is our goal, say. Then what makes these trees grow in a nicer way? If there is a hurricane, if there is a storm, there is too much rain, then don't you need sensors? Don't you need good fertilization if there is a drought, or enough water if there is drought, or if the soil is bad, we need good fertilization, or you want to look at the content of that soil water just to replenish it. So if it is not enough, so all these things can be nicely exploited through this particular, I would say, this neural network kind of thing, because That's the data. By putting the sensors, you can generate tons of data like that. That this tree, died because of such and such condition. This tree did well, such and such condition. That tree did this, such and such condition. That tree had 100 fruits, 100 mangoes versus the other mango tree. All these things, that database can be utilized very nicely, put together, and generated in a DNN model, and you can utilize that and give that intelligence to the sensors. The sensors, what they will do is they will actuate the, say if there is a pump, motor pump, or the water pump, that pump will pump the water from the well if the water is not sufficient, something like that. So these are the applications, and this is how you can do it. Okay.
So there is one more question.
Mhm.
What is the difference between Apple M1 chip and Intel chip?
Okay. Now the details. So actually I may not be able to answer that because there are lots of Intel chips, and there are a lot of what the manufacturers or the fabricators would do is they may take those chips and label it under different name. Or Apple also has a design house in it, internal design house. They can also design a chip, which I just mentioned to you. The way we did it, they can design a chip, and also they can put it in their phone. It would be cheaper, right? Because these days, what has happened is you can use SoC, SoC technology, silicon on chip, or you can use ASIC technology, right? In ASIC, you can build SoCs very easily. You can bring in the functions, different functions, and you can create a chip within no time if you have enough manpower. So things like that are possible. And so I don't know exactly what the M1 chip is, and Intel, because it's hard to unless we do the reverse analysis of the chip. It's very hard to say unless you see the data outside. There are companies who do reverse engineering and come up with which chip is what and all that. So
Sir, one more question is there.
Yeah.
How can we implement the AI techniques in battery charging of EV?
Right. So I gave you a classic example how they did it. Right. They use this machine learning technique. So first you need to have these number of cycles. When it fails, you have to do battery by battery, generate the data, and try to apply these machine learning techniques. They use what is called as Bayesian optimization technique, and that's how they did it. But there, you can explore that. I mean, that is where all the research, right? People are doing a lot of research in that, and I'm not the expert in that domain, but I can see that if I were to do that, then I would do it looking at a wide variety of these machine learning techniques. And I mean, and applying many like things like these variability concepts. How do you prune them? If you have large data or if you have small data, can you prune the data and things like that? So there are wide variety of techniques you can use.
I think the one more question is there. What is BMS system? What is importance in battery charging system?
Okay, so I think that is a little bit out of my domain, about battery charging. So, so I may not be. So I don't know the answer. I mean, you should ask the. I think there are sessions, further sessions in that area,
Yes, sir,
right?
yes, they are there.
Okay, so maybe that would be the appropriate thing to do that.
Okay, sir. I think the questions are now over, so we can come to the conclusion. An excellent session by Professor Dr.